a reason why I have a slinky here on the table, because in fact we're going to talk about the physics of a slinky today. But first I want to motivate us why we care about springs. In fact, that's all a slinky is just a spring. It's just a spring. So what do springs have to do with chemistry? And again, again, we're going to talk about springs, but I want to use a different term, and this term that I'm going to use over and over again is harmonic oscillator. And I want to talk about today, well, first I want to talk about why spring is a useful model for us for chemistry, but also I want to talk about what a harmonic oscillator is. So I kind of want to get the kind of physics of a harmonic oscillator out of the way, understand how it connects, and then apply quantum mechanics to it, to a spring, quantum mechanical spring. We'll come up with a model, right? Come up with energies and wave functions. And I'll talk about why we call it a harmonic oscillator in particular. We'll also talk about things that are called anharmonic oscillators, and I'll talk about the difference between harmonic and anharmonic. If you've ever taken music, or any understanding of music, you'll understand the idea of harmony and harmonics. It applies directly here. Okay, so what I want to talk about, why we want to do springs, is let's consider the different models, things that we've looked at so far. The first one again is the particle in a box, which is a free particle allowed to move in space. That's the particle in the box. Of course, we did a one dimension, but you can do it in three if you want it, in a cube, or in a rectangle, or whatever shape you want. We looked at free rotation, in particular of a diatomic molecule. Right, so this is particle in the box, pain in the butt, and this is these are what we call angular minimum, or what in our solutions are the spherical harmonics. So that's one motion. So this is translation. Remember, this is translation, x, y, z. This is rotation. We've talked about a particle bound in a spherical attractive potential. Well, that's the hydrogen atom. Right? This is the hydrogen atom. Right? We put an electron, allow it to spin freely around a potential, right? The nucleus that attracts it. Got some physics, that's the hydrogen atom. Right? This is what we would call electronic motion, right? The motion of an electron. And as we start to, as I've mentioned this before, there's only four ways that chemistry has motion. There's only four types of motion in chemistry. One is translation, one is rotation, one is the motion of electrons, right, which tends to be at high energy, much faster than this is rotation of nuclei, right, of atoms, right, heavy atoms, and of course translation is heavy atoms as well, heavy particles. Of course it can be an electron too, it doesn't really matter, but anyway, my point is that these are motion of objects moving around as a complete unit. And of course, in the hydrogen atom, you're fixing the atom in place, and you're looking at the electron moving around the proton. So there's no motion of the atom, there's motion of the electron. So that's different. Right? So this is internal motion, if you will, within an atom that may be contained inside of a particle in the box, or an electron inside of a diatomic molecule. Electronic motion. There's one other that we haven't mentioned, that we haven't talked about, which is the motion of atoms bound in a molecule, let's say relative motion of atoms bound in a molecule. So imagine you have you have a diatomic molecule. Again, let's do HCl. Again, we can let me get a brighter color. We have our HCl molecule. Again, we have an electron inside of this hydrogen atom that's spinning around, right? That's our electronic motion. The whole molecule can rotate, right? Or the whole molecule can translate. Right, but there's one other motion we haven't considered, which is the motion of the H relative to the CL. Right, there's this motion as well. And of course, this motion is vibration. Right, you can make your HCl molecule rotate, you can move it around, all things being equal. Right, the electrons can fly around the hydrogen and the chlorine freely, they can do their thing. But we haven't considered the fact that H and Cl can move with respect to each other. They can stretch, they can compress. Right? And this is where we're going to use a spring. So we're going to treat molecular bonds as springs. Okay? A molecular bond has some strength to it, right? Eventually you're going to be able to pull it apart so much that the atoms split apart. Right? You're going to break that bond. Right? There must be some, but there's also some force. You can imagine if you pull those H and Cl together apart like this, if you could physically do that, they'll stretch apart, and what do they want to do when you let go? They want to come back. Right? Or maybe you want to compress the bond, and what's the bond going to want to do when you let go? It's going to want to expand. Right? And the spring works exactly the same way. Let me show you that. So here I got a slinky. Come back to the slinky again. Slinky's not the best option because it's so floppy. It's not a very good chemical bond, but bear with me. But here I can imagine that imagine that we have our slinky here, our spring. It's hooked to a fixed place, right? So it's bound here by a fixed box, right? It's attached to my hand. And if I don't move my hand, eventually the spring's going to equilibrate at some length. Right, let's say it's about there, right? This is kind of like the equilibrium length of the spring, right? The spring doesn't, I mean, it's oscillating a little bit because I'm moving, but if you imagine it's perfectly still and we wait long enough, it'll kind of stay at this length, right? So what happens when I extend the spring, make it longer? Well, it wants to compress back, right? It starts to oscillate this way, right? It pushes against the motion of the stretch and comes back up. Likewise, if I compress the spring, it wants to do the opposite. It wants to stretch out. Right? And bonds work exactly the same way. Right? Bonds have some bonds are really strong, they're really stiff slinkies, and some bonds are very floppy and they act a lot like a slinky does, excuse me. But in general, the physics of this slinky will tell us everything that we need to know about a bond. If we assume that, again, bonds have some kind of stiffness, if you will, some sort of length that they like to be at, and they also exhibit forces that press against the motion of stretching and bending, or stretching and compressing. Okay, and so but what I've shown you is a spring attached to a fixed point. So what I have here is a box or some sort of object, fixed object, that I've attached the spring to. So here's my spring. And on the other end, of course, on the other end, I'm going to attach a mass, a ball of M. Right? And in the case I don't have a mass attached to this slinky, but you can treat this. It doesn't matter. You can set M to 0 if you want, or something like that. But just imagine I take this slinky and I attach a mass to the end. Right? Again, the analysis is exactly the same. In this case, I have gravity working. There's a gravitational force stretching this out, and of course, when I add a mass, that's going to add to that gravitational force. But the thing stretching this out is gravity, right? So we're not going to we're going to ignore that. So instead of having gravity, we're just going to fix a mass there, right? So this is kind of our replacement for gravity. All right, so this is the problem that I'm describing here, and the question is, well, that doesn't look like a molecule at all, because what a molecule is a mass, is a ball, an atom, say H, attached to a spring, attached to a chlorine. Forgive me that the H is bigger than the Cl, right? These are very different. These look very different. But in fact, they're the exact same problem. We can interconvert between these 2 points of view. And let me explain what that is. If you imagine the physics of let me think about it this way. If you imagine looking at HCl floating by itself, and it's vibrating like this, again, you see the H and the Cl the same way. right? You see the H move away, so as it stretches, you see the H from your perspective. So I'll draw my perspective like this. So this is my perspective, looking at the bond along the bond. I see when the molecule stretches, I see the H move this way and the Cl this way. You see it like that. They both move together. But imagine if I attached my camera, I attached the GoPro to the hydrogen atom. So it's fixed on the hydrogen atom. What would this look like to my view? Well, it would look like my H, I'm not moving. It looks like the chlorine's moving away from me. So I'm staying constant, and this is moving away. Well, it's the exact same problem as this. Right? So this is a diatomic from the point of view, not the POW, the POV of an atom in the bond. And this is the point of view from the laboratory. Right? The only thing that's different between the physics of these two systems is the point of view. Right? It's the exact same physics. So if I can interpret this, I know everything I need to know about this. I just have to change my point of view. All right, and this is just and so let's do this analysis. All right, so instead of dealing with two masses moving in two directions, that can be tricky because I need to track the position of the H simultaneously with the Cl. But if I convert to here, the H is always fixed, and now I'm moving a mass of some mass. So I only have one coordinate to track, right? Because there's only one thing moving here instead of two. Okay, so this will be a convenient way to do the analysis. And we just have to remember that we're looking at a bond, but in a slightly different perspective. All right, so let's do that analysis. I'm going to go ahead and redraw this. So here's my binding post. I have a spring, and attached to it is a mass. All right, we'll say mass M. All right. And let's say that when there's no forces being applied to the spring's just allowed to relax. Maybe it's easier to think about this in gravity, and it's pointing down, so gravity's acting on the spring. There's some equilibrium distance that the spring exhibits. We'll call it L. Right, so L is the equilibrium length of spring with no forces applied. So the spring just sits by itself. It sits at this angle. Nothing, just some equilibrium distance. All right, so what I'm going to do now is I'm going to define, let's call this L0. Sorry, L0 instead. What I'm going to define is a new coordinate, which is x, which is the length of the spring minus the equilibrium length. Right? So if x equals 0, L equals L naught, spring equilibrium. And if x is greater than 0, that means L is greater than L naught, spring stretched. And if x is less than 0, the opposite is true. L is less than L naught, spring is compressed. So this is nice because what it means is that if the spring is not exhibiting any forces, it's just at normal equilibrium, it's at x equals 0. Okay? So the origin is kind of the equilibrium length of the spring. Okay? And there's a really simple law. The force exerted on a spring is equal to minus k, I'll tell you what k is in a second, times the displacement. It's linear in the displacement. Right? Minus kx. Right? This is called Hooke's law. Right? Again, we're not doing any quantum mechanics. This is all classical. Just a normal spring, slinky attached to a box. And where k is called the force constant of the spring. Or another term for it more casually is called the stiffness. of the spring. Right? So the idea is that in order to displace the spring, let's say we want to double the length, we have to put in a force of 2 times kx. So let's think about that. So if we want to double the length, so if we want to go from x equals 0 to 2L naught, then the total amount of force is going to be minus 2, KL naught. Right? So if the spring is really stiff, which means K is large, the amount of force you need to stretch the spring is significant. And of course, if the spring is really floppy, then K is small, and it doesn't take a lot of force to stretch it. Okay? So anyway, a spring can be measured by one. A harmonic spring, we'll explain what that is in a little bit, can be measured by one number, right, K, the stiffness. Okay, and so now we have a function for force. Well, we can use Newton's second law. Which says F equals ma. And again, another way to write A is m times the second derivative of position with respect to time. Right? Remember, velocity is the derivative of position, which is dx dt. Acceleration is the derivative of velocity, therefore the second derivative. Right, so we have this formula now that the mass times the acceleration of the spring, of the mass moving, is equal to minus kx. Or we can write this more simply, that the sum of the two terms is 0. Okay, so if we want to solve for the position, the physics of the spring, which is x of t, right? We want to solve for the motion of the spring, x of t, the position of the mass as a function of time upon a stretch. We need to solve this differential equation. It needs to be mass times the second derivative of some function times plus multiplicative of a function equals 0. All right, so we don't really have the tools to solve this just yet, but we don't need any tools because we can use a slinky to figure out what the function looks like. So what I want to do is I want to think about, I want to plot as a function of time the position of the end of the slinky. So we'll call that x of t. Right? And let's see what that function looks like. Right? Let's just do an experiment. All right, so I'm going to apply a force of some sort to that is equivalent to a mass, stretching a mass on my slinky. And I want to ask the question, so imagine the mass again sitting here is connected to the bottom of the slinky. And I want to ask, what's the position of the mass as a function of time, as the slinky oscillates or slinky stretches. So I'm going to stretch it pretty far, and then let's think about how the position of the end of the slinky moves as a function of time. Goes up, goes back down, goes back up, goes back down, goes back up. Of course, you can see it's dampening like this. The oscillations get smaller. I'll show you again. Right, the first pass after it oscillates is quite large. Right, it displaces a lot. Right, almost all the way up and back down, and then the next one's shorter, and the next one's shorter, and the next one's shorter, and the next one's shorter. But it still oscillates up and down like this. So our slinky plot looks like, let's say it starts at some high position. Let's call this, I don't know what this position is, we'll call it x naught. And as a function of time, it gets, we'll say this is, well, it doesn't matter which way we go, but it goes down to equilibrium, it passes equilibrium, it gets shorter than that, and it comes back up again. Let me put this at 0. Comes back up again, goes back down, comes back up, and then again the slinky is damped, so it gets smaller and smaller over time like this, right? That's what we saw. But if we did analysis of this, what we would find is that the period or the frequency of this wave is fixed. But amplitude is decreasing in time. Now, the reason why the amplitude is decreasing, right, the question is why does the amplitude of the oscillation decrease in time for the slinky? Well, the slinky's not perfectly efficient. It loses energy over time, right? It's got to fight gravity, right? It's got to fight gravity. It's not a perfect slinky, right? So eventually the system loses energy, so it can't oscillate nearly as much as before, right? It's not a perpetual motion machine. So that's why this starts to dampen out over time. But it's a sine wave of a fixed frequency. If you just look and watch it, you can see that the oscillations, the period of the oscillation doesn't really change that much, just the amplitude. Right? That amplitude of that motion is basically the same the whole way this oscillates, right? It's just that the amplitude gets smaller. The period is the same, but the amplitude gets smaller. So this length, called the wavelength, is the same as this one, which is the same as this one, and so on and so forth. Right? It's the same wavelength. So ideally, if this were a perfect slinky, what would it look like? Well, there's no loss of energy, so the slinky is a perpetual motion machine. So we would expect it to go like this forever, like that. So what is this? That's just like it's just a sine wave. It's just a sine wave. Right, so I don't have to do any fancy math. I already know the solution of this. I just have to look at it. It's oscillating up and down at a fixed wavelength. Well, it's a sine wave. Right, so the solution to this problem, right, the physics, the motion of a slinky as a function of time, is on my next page. You can just express generally as a sine wave at some frequency and amplitude, omega t. That's the frequency of the wave, plus another term, a cosine term. And depending on where we start in our expression, whether we start at equilibrium, which would be x equals 0, or we start at a stretch, it would be a cosine or a sine, right? So it depends on initial conditions. The way that I draw it on the board, in fact, it's not a sine wave. It's actually a cosine wave, right? Because it starts at where t is 0, it's at 1, right? It's at the peak. So it's really just a cosine. But it can be a sine as well. It just depends on where you start the circle. Right, so we don't have to do any fancy calculus at all. We can just look at it and say, okay, it must be a sine wave. And in fact, it is. All right, so again, maybe you can already get the sense of why we call springs harmonic oscillators. Is that a perfect spring oscillates at a fixed frequency. It has a harmonic, which is the frequency or the wavelength of the oscillation, and the spring oscillates at that frequency forever. So this means, in some ways, a one-note wave. And this means, it just means oscillation, right? It oscillates sine cosine. Right? So a spring can be represented as a sine wave of a single frequency. Right? Notice that in real life the amplitude has a time dependence, right? Because the amplitude is getting smaller over time, right? And that's due to energy dissipation. But let's not worry about that. Right? Again, we're just dealing with spherical cows here, so we're going to assume that our springs are perfect. Our bonds, if you will, are perfect springs, so that they can oscillate forever like this. And if we find that that's a bad approximation, we can fix it later. Okay, but we'll make the approximation that bonds are harmonic oscillators. So let's treat a diatomic bond as a harmonic oscillator. Okay. We need to do a little bit more math, but it's not too hard to fix. To go from here to here, you have to change the mass. Because you're at a different perspective, you have to change your perspective on the mass. You also have to, this mass in fact is going to be the reduced mass, which is the mass of atom 1 times the mass of atom 2 divided by M1 plus M2. Okay, so the only change that we have to make is that when you look at from the perspective, lab perspective, at two bonds oscillating, that's the same as a single spring with a single mass oscillating against a block, where the mass is the reduced mass of the diatomic. All right, so let's set. Assume a molecule AB, right, could be HCl, I2, whatever you want. Let the mass be the mass of A times the mass of B over the mass of A plus the mass of B. Okay, and so that means classically that mu times the second derivative of position plus k times position equals 0 gives you a solution, right? So classically that's just the solution. You get sines and cosines. Okay. All right, we've done everything. One more thing I want to do is that I'll also define the equilibrium bond length, which is the idea of the same as the equilibrium spring. I don't know what I call it. Let's just call it R for now. All right, so R is the distance between A and B when it's not vibrating. Okay. That's all we need. Now what I want to do is apply this idea to quantum mechanics. So again, we have a quantum mechanical particle, HCl, a diatomic, right? This is something that's a particle in a wave. So this math shouldn't work, right? This math might not work for us. We need to use quantum mechanics and see how the different results are different. So again, in quantum mechanics, instead of Newton's second law, so instead of solving F equals ma for the position, we solve the Hamiltonian times the wave function equals the energy times the wave function for psi of x. We want to calculate the Hamiltonian, so instead of using Newton's second law, we're going to use this Hamiltonian, where h is the kinetic energy plus the potential energy. All right, and so it's the same process as before. We can write down the kinetic energy of the problem, and then we have to come up with the potential energy, and then just solve the Schrodinger equation. So the kinetic energy is easy enough. Looks like every other one that we've ever seen. It's minus h bar squared over 2 times the mass times the second derivative with respect to position. Right? Same as every other particle, right? Kinetic energy is p squared over 2m, or h bar minus h bar squared over 2 times the mass times the second derivative. That's never changed. Now the question is, what's the potential? Well, there's a nice, so what's the potential? Let me write that down. So what about potential? All right, well, we know the force. We know that the force for a spring is minus kx. Okay? And it turns out that the force is equal to the negative derivative of the potential with respect to position. So potential energy is equal to the integral of the force with respect to position. It's minus. Okay, so all we have to do is integrate this to get the potential, and that's really easy. That's minus times the integral of minus kx dx, which is just 1/2 kx squared. That's it. The integral of x is x squared over 2. Minuses cancel out, and you're left with 1/2 kx squared. So the potential V is 1/2 kx squared. And that's it. So the equation that we need to solve for our motion, right, the wave functions of our system, looks a little different than it does in the classical case. What we want to solve, h here is minus h bar squared over 2 mu d squared dx squared plus 1/2 kx squared. So, applying Schrodinger's equation, h psi equals e psi, we get that the second, I'm doing a little bit of algebra here, that the second derivative of the wave function with respect to the position plus 2 mu over h bar squared times the energy minus 1/2 kx squared psi is equal to 0. Okay, so let's talk a little bit about this one. So in the classical case, we had that the second derivative of the position with respect to time is equal to rough proportional to the position itself, minus the position. Right? dx squared dt squared is equal to minus kx times some constants. And here we have something completely different. We have a second derivative with respect to the position equals x squared times the function. All right, so that's a different function. That's a different wave function. That's a different equation altogether. So instead of having it as the second derivative with respect to time is equal to position, here we have that the second derivative with respect to position is equal to the function times x squared. So that's the solutions will not look like sines and cosines. Something else is going on here, right? And so solving this is tricky. It's not obvious. And I can't give you a slinky and show you what it looks like because I don't have a quantum mechanical slinky and that would defeat the purpose. So I can't really write down what I think is going to happen. Solving this is tricky, but it turns out it's exactly solvable. All right, we can actually come up with a wave function, an exact wave function in energies for this system. Right? This is an exactly solvable problem. Later in the class, if we have some time, I'll actually show you a really easy way to come up with the solution without having to do all these differential equations. There's a different way to tackle the problem, and it simplifies this significantly. So the question is what are the solutions of this? What does the motion of a quantum mechanical slinky look like? In fact, you get really, really beautiful answer for this. It's a really, really simple problem. The question is, do I want to show you the wave functions first or the energies first? Yeah, let's look at the wave functions first. Let's look at the energies first. Yeah, let's look at the energies. So again, you get some energy, right? So the system has a single quantum number. Again, remember, every quantum mechanical system is associated with a quantum number that tells you what energy level you're at. Nothing's changed. Everything's the same. We call this V for vibrational quantum number. Okay, and V can run from 0, 1, up to infinity. Okay, so it could be 0. And the energy as a function of the quantum number V is h bar times the square root of the force constant divided by the reduced mass times V plus 1/2. That's it. We often call K over mu the fundamental frequency, because this has units of energy. We want everything to be total units of energy. We know h bar is joules seconds, so this has to be per second, which is a frequency. So this K over mu square root has units of per second. fundamental frequency. We often call it omega. Omega. So we can write EV is equal to h bar omega v plus 1/2. Okay. That's it. Simple as that. It's linear in the constant, and it can take any value, any positive or negative or zero value. Now here's something very interesting. We'll look at this a little more carefully, but let's evaluate this at v equals 0, the ground state. Okay. So let's imagine what if we had a slinky, a classical slinky, like this, and imagine it's just fixed in place. It's not doing anything. Of course, it is going to do something for a while, but imagine it's not doing anything. And you freeze it out. All right, it's just sitting in a vacuum by itself. It's not moving. What's its energy? Well, it's 0, of course, because there's no motion. Right? So a regular slinky, classically, if it's not moving, nothing's happening to it, it's got no energy. E is 0. So if you call the ground state of the slinky, energy 0. But what about for a quantum mechanical one? Well, that's h bar omega, 0 plus 1/2. 1/2 h bar omega, which is not equal to 0. So here's something crazy. A quantum mechanical slinky, you cool down to the lowest possible level, and it still has residual energy left over. Right? We saw this with the particle in the box. Remember, the particle in the box doesn't have an n equals 0 level. It has an n equals 1 level, and that has a fixed amount of energy in it. You can never get rid of that energy. And a harmonic oscillator works exactly the same way. Harmonic oscillator will always have some residual energy in it. And this 1/2 h bar omega is what's called, as I've mentioned before, is called the 0 point energy. So what that means is that if you were to theoretically cool down a molecule to a really, really tiny temperature, right, really, really close to absolute 0, all your molecules in your gas phase sample are in the ground state. They're not vibrating technically, formally, right, at v equals 0. They're still vibrating. They're still moving. They still have a little bit of vibrational energy in them, 1/2 h bar omega, that you can never get rid of. It's always there. All right, and so if we were to plot these, what I'm going to do is plot position. So this is again the position of the bond, if you will. Let's set this to R. So that's the equilibrium position. Maybe it's better to do it this way, actually. So let me set it a little differently. So instead, what I'll do is I'll draw x equals 0 right in the middle. Draw x like this, and then this is energy, or potential, if you will, as a function of x of the system. Remember, x equals 0 is where the bond is at its equilibrium position. And of course, the potential energy at that point is 0, right? 1/2, or this is equal to 1/2 kx squared. So we know the potential energy of the spring is 0 there. And it's a parabola, so it kind of looks like this. Like this. And the space, how wide the parabola is, right? The width of potential is proportional to 1/k. The smaller k is, the more broad it is. And what we can do is we can look at, right, so this is the potential energy of the spring. And again, the way to think about this is pretty obvious. Again, remember that if x is greater than 0, this is stretch, and this is compress on the negative side. If we were to compress the spring, so we're on this side of the potential, let's say we compress it to here, to x prime, the derivative, remember the derivative of potential is equal to the negative of the force. We look at the derivative, it's negative here, which means the force is positive. And that means that, there's an applied force happening that wants to stretch the spring out. Meanwhile, if we're on this side, dV dx is greater than 0, which means the force is negative. This wants to compress. This wants to expand. So again, we're seeing the exact same thing that we saw with the system, with the slinky. That when you stretch it, the net force wants to bring this. When you compress it, when you compress it, the net force wants to bring the spring out, force the spring open, and when you stretch it, it wants to compress, right? Which gives you these clear slopes, right? And of course, when you're in the middle, dV dx is 0, which means that there's no force to compress or stretch the spring, right, or the bond. And so the potential energy is 0 there. And so what we can do now is we can plot our energy levels in this potential, just like we did with the particle in the box. Let me erase these just to make it clearer. And so let's go ahead and do that. Let's call this right here 1/2 h bar omega. So this is the V equals 0 state. And where is the next one at? Well, E1 is going to be h bar omega 1 plus 1/2, which is 3/2. Right, so that's going to be in like right here. One. And then where's the next one? H bar omega 2 plus 1/2, which is 5/2 omega. Right, and I bet you can figure it out that the next one's going to be a 9/2, and the next one's going to be an 11/2, and so on and so forth. So this is 1, 2, 3, 4. The important thing is that for a harmonic oscillator, that the energy spacing between two individual levels is fixed. Right? What's the difference between 3/2 omega h bar omega and 5/2 h bar omega? 1 h bar omega. 5/2 and 9/2. Oh wait, no, sorry. I have to take that back. Sorry, this is 1. This is 1. Oh, sorry, this is 7/2. I'm sorry. That's why the math doesn't work 9/2. Yeah. So they're all split by h bar omega. So the levels are equally spaced. Right? And this is why we call it a harmonic oscillator. Because the oscillator can only exist it has a fundamental note, if you will, at 1/2 h bar omega, right? That's kind of the fundamental frequency, as I said, of the oscillator. And it can exist at an additional unit of that, h bar omega, and then another unit of h bar omega, and so on and so forth, right? Remember, fundamental frequency is k over mu. And these are split by k over mu times h bar. So these are all split by h bar omega. Right? This is why we call it a harmonic oscillator. Right? That everything is equally spaced. Right? Of course, in waves, when we talk about notes like in music, harmonics are ones where the frequencies are doubled. Right? So if you have an A note, then your next harmonic is going to be twice that frequency, and then the next one will be 3 times that frequency. And here we're splitting them by, our fundamental note is h bar omega, and they're split by units of h bar omega. Right? That's our harmonic. Right, so the harmonic oscillator is this beautiful like music-like structure to it. Right? And there's a good reason why we study these is because the math is so elegant. It turns out to be very, very useful, as we'll start to see as we start to interpret this a little bit more. Now, one thing that you might notice is that for a harmonic oscillator, I can set V to be whatever I want. Right? V could be 1,000,000. Right? This could be at, well, we can talk about the energy scales of these vibrations, but for instance, for a CH stretch, for stretching C and H, this is about, that h bar omega is about 3,000 wave numbers for a CH stretch. So this gappage for this level is going, so this is going to be 3,008 watt number, so this is going to be at 1,500, this is at 45, and so on and so forth, wave numbers. And the splitting is 3,000 wave numbers. again, I can pump as much energy as I want into this, right? Because this potential goes for infinity. Right? It just keeps on growing. And so there are an infinite number of states in a harmonic oscillator. Right? You can pump as much energy into a harmonic oscillator, and it will just vibrate faster and faster and faster. But obviously, that's not true in molecules. Right? Eventually, you put so much energy into a bond that it falls apart. Right? So we know that this breaks down eventually. Right? Well, the question is, where does it break down? But you can imagine that if we get to really, really high energy, it predicts that the molecule will stay together at any energy, any internal energy you want. But obviously, that's not the case. So eventually, this potential is not going to work anymore because the molecule is no longer harmonic. So let me recap that. Is that the harmonic oscillator approximation assumes the spring is unbreakable. Right? So obviously real springs aren't unbreakable. Right? I can stretch this slinky far enough that it'll eventually rip. Obviously, if you stretch a bond far enough, it'll fall apart. So eventually, at high energy, the harmonic approximation, HO approximation, call it HO, should break down as bonds physically disassociate at high energy. Right? The harmonic oscillator predicts that they will never break. That V can be any number you want. But in fact, that's not true. Right? Eventually, you're going to put so much energy into that bond, it's going to fall apart. So that must mean that this breaks down some. Right? And we're going to have to look at that more carefully. Because that immediately should tell us, put it into question, is this even a reasonable thing to assume? Right? And what we're going to find, I'll just give you spoilers, what we're going to find is that when you're at low energy, and V equals 0, V equals 1, so on and so forth, this approximation is very good. That the actual potential of the bond looks a lot like a harmonic oscillator near the minimum. And then as you start to get further and further away from the minimum, it starts to look less and less like a harmonic oscillator. Okay, so it really depends on what problem you're doing, whether this is a good approximation or not. But it's well studied, and there's ways that we can correct for it. We'll talk about the ways that we can correct for it. Okay, because eventually, because from this, we can't predict a bond association energy, right? If we want to study a bond, we want to know how strong it is. Well, this isn't going to tell us how strong it is because this bond is infinitely strong, right? It never breaks. So we're going to have to do something about that eventually. Okay, how much time do I have? Good. So what I want to show you now are the wave functions. So these are the energies. And the question is, again, as I said about the Schrodinger equation for this problem, it doesn't really look like the equation for a spring. I mean, it does, but the solutions aren't going to look like sines and cosines. But we know that, because it's quantum mechanical, we know that they're waves, that they should have some oscillatory properties. Right? We know that we're treating this as a wave-like particle, so the motion should look like a wave. It should have some oscillations to it. And in fact, there are oscillations that appear in the wave functions, but they're not immediately obvious. And I want to show you those. So the wave functions for oscillators have a very simple formula. Again, they're indexed by the quantum of V. There's a normalization constant on the outside, which is 1 over 2 to the V times V factorial square root times this quantity. Just a sec. Just a second. I'm trying to figure out where this number. I have a label here that I don't understand. And I don't want to keep throwing labels at you guys. Page 5. Oh, okay. Here it is. I'm sorry, I just couldn't find it. Okay, so all right, so there's this, and then there's this term I'm going to index as h. I'll write down the values for this in a second. They're functions that are indexed by v, and they take in a function alpha 1/2 to the x. I'll write what these are in a second. And everything is multiplied by delta e to the minus x squared over 2. Okay, I'm just going to write a few things here. A is equal to the force constant times the reduced mass over h bar squared. Okay. And then these HVs are called Harmonic polynomials. And I'll just write down a couple. There's a formula for calculating them, but you won't need that many of them for this class. I'll just write down the first couple. So HO of alpha 1/2 x is equal to 1. So that's easy enough. If v equals 0, this just goes away. It's just 1. Easy. The Harmonic polynomial for the first excited state, v equals 1, is equal to 2 alpha 1/2 x. For v equals 2, it's equal to 4 alpha x squared. Is that right? Yeah, minus 2. And H3, just do it for these, alpha 1/2 x is, just a second, let me think about this for a second. It's going to be 8, I'll just write a next line, 8 alpha to the 3/2 x cubed minus 12 alpha to the 1/2 x. All right, so anyway, they're just polynomials. Right? If you notice, as you go up in levels, you go, so the order of the polynomial is just the quantum number. So in the ground state, you just have a constant, 1. In the first excited state, you multiply your wave function by a linear function, x. You have x times e to the minus x squared. In H2, the second level, you have an x squared, a quadratic polynomial. So you have roughly x squared times e to the minus x squared. And then for the third level, you have a cubic, right? And you can imagine for the fourth level, you have a quartic, and for the fifth level, you have a quintic, and so on and so forth. Right? So basically, the wave functions is e to the minus ax squared times this polynomial, right, in x, in the position. All right, but the real take-home point is this right here. E to the minus x squared over 2. Right? This is what's called the Gaussian, this is called a Gaussian function. That's the technical term for it, but you guys probably know it as a bell curve or a normal distribution. So the wave function, let's look at what these look like. So if we look at the ground state wave function, or v is 0, this again goes away, so you have some number, in fact this is 1, times e to the minus ax squared over 2. It's a bell curve. So here I'll draw my potential again. I'll draw my v equals 0 state right here. This is at 1/2 h bar omega. And the wave function looks like a bell curve. So it's centered at the center. And then lowers down like this. And actually kind of trails off. Like this. That's the wave function for the ground state. Okay, so it doesn't look like a sine wave at all. There's no oscillatory behavior to it. But you can imagine, remember, a wave function only tells you about the probability of where to find something. So every time it'll give you an average, right? On average, the bond is at the equilibrium position, right? The mean of a normal distribution is the peak, right? This is the mean, right? But if you think about the standard deviation, this distance here, the square root, we know this one because we did it last in class, or we did in the problem set, is x squared minus x, right, which is not equal to 0. Right, so if you think about this system in time, on average it's right in the middle, it's not moving. But if you think about it, every time you take a measurement, it's going to be somewhere on this distribution. And so if you measured if you measured the position if you measured this as a function of time, so if we take this and now measure t versus the wave function at a specific time, right? So we make a measurement of the position. Let me say that. The position of the bond is a function of time for the ground state. We make that measurement. What do we see? Well, sometimes it's going to be positive, sometimes it's going to be negative, sometimes it's going to be in the middle. And in fact, what it does is it just goes like this, right? It just oscillates in time like that. Right? So in time, it looks just like a harmonic oscillator. The system is vibrating, right, at this frequency, 1/2 h bar omega. This wavelength is c over h bar omega. So that's the frequency of the, sorry, it's actually c over omega. I apologize. C over omega. So that the bond is oscillating back and forth, back and forth, back and forth in time at the frequency of its energy. Right? It's a wave, it's a pluck. And the wave function only tells you what you expect from the measurement. And all it says is that you have an even distribution. It can be either short or long, and on average it's right in the middle. Okay? But in time, it still oscillates in time. Right? It's still an oscillator. Right? So this is, again, a time-dependent picture. We have time explicitly encoded here. And here we're not looking at time at all. We're averaging over time. Right? This is no time at all. This is what we call a stationary state. Right? We're not expecting time. What we want to measure is the position, the statistics of the position for that state. Right? And that gives you this natural bell curve. Right? And that bell curve leads naturally into a sine wave in time, when you include time. Okay, so the physics that we see here are the same as before. We're just looking at it from a different perspective. All right, so let's go to the next one. V equals 1. So this is at 3/2 h bar omega. All right, and let's think about what the wave function looks like. Well, we have this e to the minus x squared, this bell curve, but it's multiplied by an x. So this function, I'll just write it, let me write it over here. So the wave function of the first excited state kind of looks like x e to the minus x squared over 2. All right, so this function, the x is odd, and this is even, about x equals 0, right? This doesn't change sign, obviously. X obviously changes sign from negative to positive. So what we have then is something that looks like this. It's negative less than x, and it goes to 0, and then crosses like that. Actually, it looks a little more peaky than that. Let me see if I can make it a little better. Maybe I have a nice drawing of it. Yeah. It's kind of like, so it actually descends out like this. Like that. That's a really bad drawing, but you get the picture. That kind of looks like a sine wave. Right? It has a slightly different shape because the e to the minus x squared, but it changes sign and it has that kind of oscillation behavior, right? This is kind of like, if we think about the particle in a box, if you remember the wave functions for particle in a box, the ground state wave function looks like a half a period of a sine wave, and the first excited looks like a whole period, just like here. And then we can keep going, right? The next one is going to be some term x squared minus 2. Right, we have another function like that, and that turns out to have two nodes, I mean. It's positive on the outsides, and then negative in the middle. Yeah. And so on and so forth. Right? So the product of the Harmonic polynomial h of x times e to the minus x squared over 2 gives an oscillatory function that only oscillates within the bounds of the potential. All right, so if the wave functions look like sine waves, they would just oscillate forever. Right? I don't want to draw it and ruin my picture, but right, if the solutions were sine waves, it would just look like this forever, right? Like that. Right? But if you notice that these also have, again, fixed wavelengths and oscillatory behavior, but they don't oscillate outside the bounds of the potential. What happens is that at the potential, outside of the potential, these functions just eventually decay to 0 because of the e to the minus x squared, like this. Like this. Okay, so the oscillation only occurs inside the potential, and outside of it is just exponentially decayed. So let me write that here. So inside potential, wave function looks like a sinusoidal function. And outside, psi of x decays like e to the minus x squared. Okay. So inside the potential it oscillates, and then outside it decays out. It stops oscillating. Okay, so it only oscillates where it matters. But these are the exact solutions, so this is the way that the physics of harmonic oscillators work. Right? You can imagine you can keep going up in angle, in energy. Right? The next one, I'll just draw it briefly, is going to look like 2 whole periods of a wave. It looks like this. Something like that, and so on and so forth. Very, very similar to the harmonic oscillator, except now we don't have sines and cosines. We have these interesting bell curve-like functions instead that oscillate. Okay, so again, everything still functions like a wave. We have nodes, we have frequencies, everything is normal like we expect, but the functional form is just slightly different. Like it looks more like a polynomial times an exponent. Okay, what time is it now? All right, I have a couple more things I want to mention, but I don't know if we really have the time to really jump into it. Let me see. Something I want to mention, and we'll do the analysis of this in class on Wednesday. I want to redraw something real quick for you. So what I want to look at is just the ground state of this function. So I'm just going to draw a little bit of my potential. And I'm going to draw my wave function like this. Starts here in the middle, and then kind of decays out like this. Decays out like this. I'm going to draw this axis like this. So psi of x goes to 0 as x goes to infinity. Okay. So again, this is the wave function. The square of the square. You can also represent it as the square of the wave function because the square of e to the minus x squared is just e to the minus x squared. So you can also look at this as the probability of the position of the harmonic oscillator. So let's think about a classical oscillator with this energy. Okay, so let's imagine I have my slinky and I give it this energy. Okay, this much energy. All right, so let's imagine I give it this much energy, and let's say I start it stretched. Okay, so I start here. Okay, what happens to the position of the bottom of the slinky as a function of time? Well, if it were perfect, right, it decompresses. I'll do it. Let me stretch it a little more. It's stretched. I've stretched it, so I'm here. I'm at the stretch position. Now it wants to compress. It compresses. And what it does, if it were perfect, is that it rolls in time from here to this point right here. Right? Energy is conserved, so if I have this much energy into it, it can't go any further past this point. So a classical spring will go from here and here, and it will oscillate back and forth forever. Right? It'll just go back and forth, back and forth, back and forth. Okay? And of course, if I stretch it further, if I stretch it here, then I know when it oscillates, it's going to compress and stop right at the other side of the point, right? By conservation of energy. Okay, so what that means is that if I have this much energy in my spring can't exist outside the potential, right? I can't stretch the spring out here because I don't have enough energy for it. In order to get the spring this compressed, I have to give it this much energy, right, to get it at that position. Okay, that's classically. But remember that the wave function quantum mechanically, the probability of finding a particle in a region is equal to the integral of the psi squared in that region. So if I were to calculate, so let's say the probability, let's call these 2 points x2 and minus x2, or let's call it x1. x1, right? These are where I stretch my slinky. Probability of finding the bond at length between minus x1 and x1, and between those regions, I'll just do it like this instead. That, with this amount of energy, so that would be at v equals 0, right, the ground state, is equal to the integral from minus x1 to x1 of the ground state wave function times times the wave function itself, right, psi squared. Right, that's the probability of finding it in this region right here that I've crossed out, or I'm shading. Right? So this is the integral from x1 to minus x1 of psi squared ds. Okay. But if we look at, but the fact of the matter is that, I'll rewrite this bigger, is that e to the minus x squared goes to 0 only if x goes to infinity. So in fact, there is a little bit of area under the curve outside of the bounds, the classical bounds of oscillation. So a quantum oscillator has a probability, some probability of being here, because there's some area under the curve because it hasn't gone to 0, and some on the other side as well. So the probability, what this means is that this is less than 1, right? The probability of it being anywhere is 1. So the probability of it being within the bounds that a classical spring would move between at that energy is less than 1, because there's a little bit of area in the curves outside of the function. The probability of the bond existing at classically forbidden lengths is going to be equal to the integral from negative infinity to minus x1 of psi squared plus the integral from x1 to infinity, that's here, x1 to infinity and minus infinity to x1, minus x1, right? I'm just integrating those two blue regions. It's not equal to 0. Right? The area under the curve of the region that is allowed for a regular oscillator to be, a spring, a normal spring, a slinky to be, does not constitute all the possible positions of a quantum mechanical oscillator to be in. Quantum mechanical oscillator can exist outside of the potential bounds. So it, in fact, can be at longer distances and shorter distances than you would predict for a spring. Right? So what we say is that a harmonic oscillator can tunnel out of the potential. Right? Remember, the potential just tells you classically, at a given energy, how far you can stretch the spring or compress it. Right? Any more compression, any more stretch, you have to increase the energy. So if you fix the energy, there's only a certain distance the spring can compress or extend. But in quantum mechanics, at a fixed energy, the harmonic oscillator can be at any position. So you can have a harmonic oscillator that has a non-zero probability. Again, it's in ground state, it's cold, it's in the ground state, vibrational state, nothing exciting is happening. And there's a probability that the atoms are infinitely apart. Not infinitely, but one might be on Mars and one might be on Earth. There's nothing, it's the probability that is tiny, but there's a non-zero probability of that existing. So there is always a chance for bond to be longer or shorter than classically predicted. This idea that a bond can tunnel, right? That a bond can exist outside of the energy bounds that you give it classically, is something that that is extremely important in chemistry. Hydrogens, for instance, in hydrogen bonding, proton transfer, Lewis-based chemistry, things like that. A lot of those reactions and a lot of that chemistry is driven by, imagine a CH stretch or an OH stretch. That hydrogen on an O stretching, it's a very kind of loose, wobbly bond. That hydrogen can tunnel out of this. Imagine it can tunnel away from the atom that it's connected to, the O it's connected to, and find itself on another atom somewhere else. Right? And you don't have enough energy to get over that potential, but it can go through the potential because there's a little bit of probability on these wings. Right? And so that drives a lot of really, really interesting chemistry, which I hope to show you guys in future classes. Okay, that's all I have for you today. The take-home exam next Wednesday. I'll post the solutions for the practice problems on Wednesday. And have a nice day. I'll see some of you in lab tonight, maybe if you're working tonight. And I'll be there Tuesday and Wednesday morning. Take it easy. Have a good one. Hey, you too. Thanks.